Alright, hey guys, what is going on? We are now going to talk about a matrix theory for quarks. We're going to see how spinors get involved with our gluons. Again, spinors are describing our quarks. And this is going to be fun, this is going to be great. Let's go ahead and get started. But before we get started, make sure to hit that like and subscribe button. Become a member on this channel. You can also become a paying member where you get all the notes on Patreon. Okay, with that being said, two more things. One is that if you become a member now, I am going to put your name in front of the content before the content actually starts in future videos. So there's that. Another thing, life sciences. We're going to start life sciences starting tomorrow, and that's going to be fun. It's going to be great. Now let's go ahead and get started. All right, so we have a solid foundation now of what makes a theory an abelian versus a non-abelian gauge theory. The abelian versus the non-abelian part gives us the matrix valued field, and the gauge part that gives us the invariant physics, right? So it being a gauge field means that no matter how we look at the physics, it's always going to be the same. The laws, the equations of motion are always going to be the same. The non-abelian and the abelian part is going to be given to us by these matrices. These matrices are these T matrices, right? So these things are, if we look at them, again, this thing here is a mu can be thought of as this thing that, or a mu a, right? This is a function. This is going to be, say, T1, a x1, and a y1, and so forth. And they're going to be functions of tx, y, and z as well. These are all functions. Right, so we have this thing, this vector, or this function, right? These are functions of spacetime, and they have spacetime components. And the A, again, is assigned to a specific matrix. And that matrix in quantum chromodynamics is our Gell-Mann matrices, right? So now here they are, the Gell-Mann matrices, right? So the Gell-Mann matrices are these guys here. This is when A equals 1. This is when A equals 2, and so forth. And this A is going to be this A right here. We're calling them lambda because TA is going to be equal to 1/2 lambda A, right? So we're just excluding the 1/2 for right now. But we can see how this is a non-abelian theory through a simple example now. If we take 1 and 2, right, these two guys, we get this guy right here. And so this guy here is right here. We do 2 and 1 then. This guy here is right here. And then we take the commutation relationship. We get this, right? And then we get this guy right here. And so more generally, we can do a similar calculation to see that we get these structure constants to maintain this Lie algebra, right? So this is a Lie algebra for SU3. We're not going to get into Lie algebras in too much depth, and I want to. I'm developing a series on diving into Lie algebras, and that series is going to follow this book. This is a really good book. This is Lie groups, Lie algebras, and some of their applications. And so I have some templates working, some notes working on this. This is very insightful. We're going to get into Coxeter diagrams and all that kind of fun stuff. But and root spaces, this is necessary in understanding modern physics. Anyways, that's going to be a separate playlist for right now. We're just trying to maintain this structure. This is a Lie algebra for SU3. Okay? And so to maintain that structure, we have to define all these constants. Right? So these constants sort of in some sense give us sort of the Lie nature, the Lie algebra nature of these matrices. There's 512 possible structure constants, but due to antisymmetry and repeating indices, any structure constant that has repeated indices, that's going to go to 0. And then because because of the fact that these are antisymmetric also, is going to collapse our 512 possible structure constants down to 9 unique structure constants. So there's that. So these are matrices that we use to develop our matrix-valued gauge field. So recall that we had looked at this equation here. This was our matrix-valued. From our matrix-valued gauge fields, we are able to create a field strength tensor, right? Our field strength tensor is this guy right here. But with all the t's here, right? So this thing here, this last part here, this last part here is G sum over B and C, A mu B, A mu or nu, C, T B, T C, right? And so this is going to be TA, and A, again, that's going from, where A is going to go from 1 to 8, right? So we can see that this thing here is a matrix because of this. This thing here is a matrix because of this. And so this thing here is a matrix because, again, of this. And so what we have, so we called this last term the self-interaction term. So in our economic model, this term corresponds to how different commodities influence each other's value. The bananas and the cuties, for example, influence the value of apples in our early economic model. So we've talked about this, where A stands for apples, B stands for bananas, and C stands for cuties. The value of those affect each other. So that's what we say. That's what when we're saying that these interact with each other, we're saying that the value of all these commodities are interacting with each other. They affect each other. All right. So, and then we had our covariant derivative as well for our QCD model. That was this thing right here. So, and then this appendage to our covariant to our standard derivative took into account when we looked at in the last video in the economic model, this thing sort of accounted for how that value is measured, right? So you have this value, and that value changes over space and time, but how that value is measured also has to change. And so that means that not only is the value changing, but how the value is measured is also changing in space and time. Okay, so now we want to get into quarks because we're developing a matrix theory for quarks. Quarks are spinors, okay? And so we need to understand what our Lagrangian is with spinors involved, not just with the gluons. Again, the gluons being these guys right here, right? So it's worth recalling from our twistor series, which is also growing. I have some videos on that coming out as well. We're going to dive into split quaternions next, which is going to be super fun and interesting. But that's beside the point here. Here we have a space-time point, okay, and it's got a component. It's got a time x, y, and z point. And here we're summing over space-time, right? Here we're summing over space-time with these sigma matrices. Here we're not summing over space-time. Here we're summing over just a label, right? This is just a label. Each label is attached to a Gelman matrix. And what we get is this guy right here. And so because we're just summing over a label, we can't really make sense of breaking this thing down into spinors. But here we were able to do that because these are space-time indices. And so the spinors, again, their outer product is what gave us this 4 Weyl vector. Right? And their dynamics is given to us by the Dirac equation. right? So these fundamentally are different procedures. In the case of developing the spinor formalism, we sum over spacetime indices, whereas in the case of the non-abelian gauge theory, we do not. Rather, we're summing over labels, where each label is associated with one of the particular Gell-Mann matrices in the context of QCD. In QED, we're summing over labels where each label is associated with a Pauli matrix. So now we wish to start throwing spinors into the mix. Spinors, as we've seen in the twistors and series, or is it in the twistors and spinors series, are the result of a decomposed 4-Weyl vector. All right, and their dynamics is given by the Dirac equation. And here's our Dirac equation. The reason we say that the Dirac equation dictates the dynamics of spinors is because the Dirac equation is a 4-component object given to us by the gamma matrices, just as the Dirac spinors and Majorana spinors are. Again, if you're not familiar with Dirac spinors and Majorana spinors, you can go on to my twistors theory, or my twister theory playlist, or twistors called Twistors and Spinors, where you can look at that as well. So we can see how the Dirac equation is related to the Klein-Gordon equation, and this is going to be interesting to note. Right? So if we define this Dirac operator in this way, excuse me, we can also define its adjoint. Right? So the adjoint of the Dirac operator is going to be just the complex conjugate here. And when we take their product, we get this thing here, and these guys get canceled out, and we get this guy right here. If we continue with this here, right, so this is going to be, so this thing here is this bit right here. So the way we can make sense of this is we have 2 of them, right? So it's going to be 2 times them, but then take 1/2 of that, right? So we haven't really done anything. But now, because we've done this, we can add this chunk right here. This chunk right here, right? This is going to cancel out with this guy, and we're going to get this guy with this guy, and then we have so because we've added this, so this is really not adding anything, right? And so when we do this, then we are able to, this is our commutator. The commutator between these two things is going to be 0, but the Poisson bracket, this is the Poisson bracket between the two, right? And so when we do that, we get this. The Poisson bracket between the two is going to be this. Not Poisson bracket. Yeah, Poisson bracket, yes. If you're not familiar with this, just take it for my word right now that the Poisson bracket between these two things is 2 times the metric. Metric then raises the index, and 2 cancels with the 2, and we get this. And so this thing right here, this is the Klein-Gordon equation, right? Because this is the Klein-Gordon equation. And so we can see that the Dirac equation is something like a square root to the Klein-Gordon equation. Not really, because we have this thing right here, but it kind of looks like a square root thing going on. Kind of like how spinors are the square root of vectors. And so we can sort of see how the Dirac equation has similar oscillatory behavior to the Klein-Gordon equation when we apply its adjoint, right? So the Lagrangian for such a system now is proposed in this way, right? Where we have the bars, the psi bars on the left side of psi and psi on the right side of psi bar. We can apply the Euler-Lagrange equations, right? So the Euler-Lagrange equations are going to be, that's this guy right here. So the derivative of L with respect to psi, we'll call this psi, right? And we'll call this guy psi also. Psi bar, right? I think I need to make this a psi bar. Oop. This becomes a psi bar. And this is just, right, this is just this guy right here, because these guys, this here, along with all this, that's just a constant that's right here. And then this, with this, that's just the constant that's right here. All right, and then we can actually, I don't want to confuse us. This is actually not, forget these arrows. Those will get erased when they get put in the notes, but this is, because this bit right here, right, so this, when we take the derivative with respect to the derivative, we get 0, right, because there's no derivative of psi bar in here. And there's no derivative of psi bar in here. So this 0 here is right there, and then this right here is right here. Okay? And so we've developed, or we've regained our Dirac equation. Right? So our spinor is this thing, right? So we've just rewritten this. We've taken psi bar out to the left and psi to the right, and we get this part. We have to promote our derivative, our standard derivative, to our covariant derivative, because we're talking QCD, we're talking non-abelian gauge theory, or gauge theory in general, right? So this is the gauge part. So this is our spinor part, this is our vector part, and these are our gluons, these are our spinors, right? So these are gluons, these are our quarks. And so the dynamics of the quarks comes from this green highlighted part, and the dynamics of the gluons comes from this red highlighted part. And so we have our gluon fields, and then our spinors. And I've sort of described them as gears here, because I'm following up with the gear analogy from our economic model in the last video. But this is the point here, is that this is now our QCD Lagrangian. Okay, so we add the covariant derivative to the spinor part of the Lagrangian because we need to accommodate for the non-abelian nature of this theory, or the gauge part, the gauged nature of this theory. And so recall that when we had used the Euler-Lagrange equations on the non-abelian field strength tensor, we got here was our Lagrangian. We got this thing, and then from here we got this thing, right? This was our covariant derivative, where the off components, we have off components of this matrix, and we have on components of this matrix, and we can see where the structure constants come in also. But the point here is that we have this is our matrix, right? This is a matrix. This is a 3x3 matrix, which is interesting, right? So this is going to be a 3x3 matrix. This is a 4x4 matrix. So how do we multiply a 3x3 matrix by a 4x4 matrix? That's the next part here, right? So we have to use a tensor product. So when we're writing this Lagrangian, we have to be very clear here. We have to see that our Lagrangian, our QCD Lagrangian, is not, to be totally clear, it's psi bar, right? I'll just copy this. I gamma nu tensor product, right? Tensor product d mu minus m psi. And then we have plus our 1/4 g mu nu, g mu nu a. Right, so this tensor product here is the interesting part. So what we're going to do now is we're going to say, okay, I'll erase this really quick. We define now this Dirac operator. Dirac operator we're calling this, right? So what we're seeing here is that here it is. Here's our Dirac operator, right? So this is going to be psi. So our QCD Lagrangian now, QCD Lagrangian, is equal to I d, right? And actually, I'll erase this really quick. What it is actually, it's psi I d slash psi, okay, and then plus r 1/4 g mu nu g mu nu a, right? So, okay, this is now the spinor part. So just looking at this really quick, let's actually go down here. This part here, this was 4 by 4. This part here, this is 3 by 3. This is the space-time part, right? Or not space-time, but this is not space-time. This is, I have it written down right here. This operates on this particle's spin properties. This operates on the particle's color properties, okay? This thing is, and there's just mixing, right? The mixing is given to us by the tensor product. So this is quite interesting. If you just think about this for a second, right? We're defining this new operator. It's not totally new, but we're defining this operator that's in our Lagrangian now. And this is, right? This is how we're thinking about things. We can add the I in front. It doesn't really matter. But the point here is that now, so we look at this now as in full-fledged form, right? This is our t component. This is our x component. This is our y component. Here's our z components. And here's our z component. This pen is so annoying sometimes. But anyways, so we have now this, we have this thing. Okay, that's the same thing as this. The temporal component, this is just copy-pasted. Forget this. But the temporal component is this thing right here, right? And the space components are these guys right here. And so we have these guys and these guys. When we do the tensor product, because this is not a matrix product, we don't, this is what that looks like. So when you do the matrix product, right, you're multiplying row by a column and then row by a column and all that. Here we're just literally multiplying this by this, this by this, this by this, this by this. This is almost like a scalar product between the two matrices. This is a tensor product. And so when we do that, we get these guys, right? So here's where the mixing, the fun and interesting mixing is going to happen for our quarks. I'll erase these guys really quick. These are 12 by 12 matrices, because think about this. We have a 4 by 4 matrix, right? This is a 4 by, or this here is a 4 by 4 matrix. Okay? But these guys are 3 by 3 matrices. So you have a 4 by 4, and inside of the 4 by 4 you have 3 by 3s. Right? So 4 times 3 is 12. And so so our covariant derivative then, right? So here's our covariant derivative then. Here's our matrix for our covariant derivative. If we just take one of these, right? If we just take where this guy I is equal to 1, right? If we just take where I is equal to 1, we get this guy right here. And this is where the mixing comes into play. We can either look at this as a 4 by 4 matrix, or we can look at it as a 3 by 3 matrix. Okay, and when we do that, if we're looking at this as a 4 by 4 matrix, the 4 by 4 structure of the matrix operates on the particle's spin properties, and the 3 by 3 structure of the matrix operates on the particle's color properties, right? This is going to be color properties. Color properties. And so we have particles, antiparticles, up, down, and then we have red, green, blue. And the spin properties, that's where we see the mixing, right? The mixing between right here, right? We see this mixing of these guys. So this is our matrix theory for quarks. This is how we're going to understand the covariant derivative in terms of understanding the dynamics of quarks. So we could see how this can get ugly pretty quick, right? Because this is just half of this, right? This thing is just this right here, and we have two of them, right? We have this one here and this one here, right? So we have two of these things. It's a 12 by 12 matrix because this is about 6 by 6. The other side is going to be, the side down here is going to be 6 by 6 also, so it's going to be 12 by 12. So I'm not going to write that whole thing out because that's kind of unnecessary thing, I think. But we can see in for time, this is what our matrix looks like. And again, these are 12 by 12 matrices, so it's going to go all the way down. Because again, these guys here are 3 by 3, right? So if this is a 3 by 3, this is 3 by 3, this is 3 by 3, we're going to get 12 by 12, right? Because we have, again, 4 components that operate on spin, 3 components that operate on color. 4 times 3 is 12. And we're doing a tensor product between spin and color. That's what this is, right? It's a tensor product between spin and color. And for our space components, this one is the same thing that I had up here. But then we have I took the liberty in writing out these guys as well. And so these are so again, these guys are, when we add these up, right, because what we have to do now is we have to add them all up now, right? So all of these guys here, we add them up, right? So this is 12 by 12, this is 12 by 12, 12 by 12, 12 by 12. That's what all these guys are. So we add them all up. So we add them all up. And when we add them all up, we get our Dirac operator operating on our quarks, right? So again, and then we have the mass term, right? So the mass terms, our mass term is also a 4 by 4 matrix, but because this is just being multiplied by the identity, nothing really that exciting happens. But yeah, so our Lagrangian then, our QCD Lagrangian then, is going to be this guy right here. It's going to be, we'll put the I in the definition for D, because that's okay to do. My gosh, this pen is just so annoying sometimes. So this is our spinor part. Spinor part. This thing is a 12 by 12 freaking matrix, right? So let's. This is a 12 by 12 matrix, right? So 12 by 12. And the reason it's 12 by 12 again is because we have 4 components for spin, and we have 3 components for color. And we have the mixing, we have a tensor product mixing between the two. Right, so tensor product mixing between spin and color. And then we have our gluons, right? So 1/4 G A mu nu G mu nu A. And this guy here, well, these are 3 by 3 matrices, 3 by 3. And this is our gluons. Gluons. And So there we have it. This is our Lagrangian QCD that we have so far. And so just to cap off some stuff, we had developed our derivative, our covariant derivative. That gets put into this thing right here, which mixes with our spin, right? So again, this mixes with spin. So this is color, this thing spin, and then this thing gets put into here for when we start developing a functional or a generating functional. And so yeah, that's we haven't talked about this yet, but that's the framework that we're looking at. That we're looking at how we are getting spin mixed with color charge to describe a matrix theory for quarks. And so with all of that being said, the next things that we're going to go over are gauge fixing and adding ghost terms. And hopefully that'll get us close to Halloween, because I think that'll be a cool match. So with that being said, make sure to hit that like and subscribe button. I'll see you guys in the next video.